so many people again visiting us here at Utrecht. Unfortunately, Rogier is not able to come, but I think we will manage. And today we are continuing a topic on statistics education that Lonneke has started 2 months ago. And Arjen de Wetter will be presenting on teaching inferential statistics. He is working at Graduate School of Education in Leiden University and have been, after master's thesis in economics, have been working as a mathematical teacher and as a lecturer in statistics for university students in Amsterdam, and then defended a thesis on statistics education specifically, and now works at university and continues research. So,
thanks for your introduction. I have my own mic, I believe. A couple of months ago, good afternoon everyone, this was one of the headlines. Ook veel ouders zijn smartphone verslaafd. Also many parents are addicted to their smartphones. Are you addicted to your smartphone? No. Anyone? No. Actually, what it says is that the NOS, Youth News, asked more than 500 children about their opinion about their parents' phone use. 1 out of 3 children, 1/3, in the research says that parents are addicted to their smartphone. So this is an example of a statement, a conclusion, about all parents in the Netherlands, I think, but it's based only on a sample, right? 500 children. And we often see this in the media, that statements about the population are based on a sample. Extreme example, where statements are made and, well, they're not, that sound generalizations is fake news, where they kind of screw the data, or even there's no data at all for the conclusion. And today my central claim will be that because of the societal importance of inference, we see often inferential reasoning in the media, in daily life, we should start early introducing statistical inferential reasoning to students already in primary education. And then develop a learning path that starts informally and ends more formally, depending on the level of education of students. So my question today is how to teach inferential statistics. Well, as Anna said, I have a PhD in statistics education, and my PhD research focusing particularly on informal statistical inference, I come back to that term later on, for teacher college students and primary school students. So I have expertise for primary education. I've been a lecturer and assistant professor in methodology and statistics at university and taught statistics to university students. And I think I also have some knowledge about how to teach, or some ideas how to teach statistics at secondary education, but fortunately Marianne is here as well, who can bridge the gap between primary education, my knowledge from primary education, and higher education, and actually I use her ideas as well in the learning path. I would like to get to know you a little bit, and rather than having you introduce yourself one by one, I would suggest to have a show of hands and a couple of questions. Who's involved in mathematics education or research or teaching in primary education? 2, okay. Secondary education, so that's the majority. Higher education, okay, about half, a third maybe. Who's involved in teaching statistics or doing research on statistics education? Okay, wow, that's nice, almost half. Who is familiar with Curriculum.nu? Who's not? Curriculum.nu? Curriculum.nu? Anyone not familiar with? Okay, that's good. I think I have a 4th question. Who uses inferential statistics in daily life, work?
Daily life.
For work, yeah, okay. I'm in my corner of my, I see the door open. Shall I close it? Yeah, it's distracting me a bit. Okay, so many in secondary education and many also involved in some kind of statistics education, teaching or research. Well, today's goal for me would be to inform you about how you could teach statistics, but also get your feedback on a learning trajectory, and I find it a bit hard to pronounce, so I also call it a learning path. And to have your feedback, because it's just a draft. So I hope we have plenty of time. I plan to have 45, 50 minutes of presentation. If there are any clarifying questions, please ask. We have plenty of time for the discussion afterwards. I will first present my PhD research. That will be the first half, and then I will continue more practically to the learning path for inferential statistics. I forgot to ask who is involved in vocational education, mathematics, teaching or research. MBO. Oh, I have some ideas about that. Maybe I can provide me with feedback on that then. Okay, given the societal importance of inferential reasoning, in my PhD research, I took as a starting point that we could introduce primary school students with inferential reasoning. And one way to introduce primary school students to inferential reasoning is by means of informal statistical inference, ISI. One definition often used by Ben Swie, our very own Arthur Bakker, and Katie Makar. They visited Utrecht University recently, right? Ben Swie and Makar. Is a generalized conclusion expressed with uncertainty and evidenced by, yet extending beyond available data. And we can see three components in this definition. Firstly, it's a generalized conclusion. So that implies it should go beyond the description of the sample data towards a conclusion about something wider beyond the sample, maybe an individual or often a population. That's what I do in my research. I take a population. Secondly, it's evidenced by available data. So the generalization should be based on the data, not solely on your own opinion or your grandmother's opinion or whatever. Thirdly, it's probabilistic. So there's always in your generalization some amount of uncertainty involved. So that implies that you need to have some understanding of sampling variability. My sample results could be different from another sample. You need to have some understanding of sample size. 500 children, 500 penwords, is that large? Is that not so large? Also about sampling methods. Those 500 children, how were they selected? That altogether informs your uncertainty. It's informal statistical inference. Well, there's no sharp divide between formal and informal statistical inference, but there are some differences. The quantification of uncertainty is, you don't always have to quantify your uncertainty. There are no standard procedures for your inference. The representations you make, or you can choose from, or the procedures are more variable. But all in all, Makar claims that it's continuum from informal to formal. We'll also see in the learning path, it starts really informally and it ends formal. If primary school students are going to learn informal statistical inference, of course their teachers are the ones who are going to introduce the students to ISI. Then these teachers have to have appropriate knowledge of ISI. And that's the starting point of my PhD research, to see how we can foster the ISI knowledge of pre-service teachers for primary education. I will present a short overview of my research. First, the design and the setup of my research, and then some highlights of the results. I conducted 4 studies. The first study was a survey study. Yes, Chris, it was, right?
Is it part of the curriculum at primary school right now?
No, it's not. Very good question. Not yet. Okay. But Curriculum.nu mentions that primary school students in the future should know the difference between sample and population. secondary education, lower secondary education, be critical about conclusions in the media, among which the representativeness and reliability of conclusions. So in the new curriculum, they hope there's more attention for the soundness of statistical conclusions, for example, in the media. Yeah. My first study was a survey study to explore what knowledge starting pre-service teachers have. So they enter a teacher college, what knowledge do they have? It was a questionnaire study with among 722 students, first-year students, 7 teacher colleges, to measure their pre-existing knowledge. So I could build on, in later interventions, on that knowledge. Second was an exploratory study in 3 classes of first-year pre-service teachers. And I also used that information for the larger study, which is the third, bit combined with the fourth. I come back to that. And the third study, it was a larger intervention, but still a rather short one. Actually, it was 5 lessons. And I implemented it in 1 class of second-year pre-service teachers, just regular teachers, and rather short. And I chose to work with regular pre-service teachers and a short intervention in order to facilitate the implementation of the intervention. When I would have used a very long intervention, it would never fit in regular curricula of the teacher college. So this strengthens the ecological validity of my research. Also, I work with regular teachers rather than volunteers, because I think it's for all students and therefore for all teachers relevant to know something about informal statistical inference. So a rather short intervention. I'm sorry, I thought my research question would come up. And a research question was, how does their knowledge develop during this intervention? And I used pre- and a post tests to see how their knowledge developed. Used qualitative data of the written work, of class interactions, group interactions, to also pinpoint what activities actually helped in this development, which I hoped to find. 5 lessons, and the first half concerned the pre-service teachers' own knowledge, and I used 3 activities. And the first one was to create awareness of that there's a lot of inferential reasoning going on in life. So what I had to do was to look up in the media to search for an example of an inferential claim and to write a critical evaluation of this claim. Is it a valid claim? What do you think of the sample? How about the uncertainty involved, etc., etc. Next, a central issue in inferential statistics, you might know, is the following. Let's take the example of those 500 kids, of which 1/3 indicated their parents were addicted to their smartphone. So we have 1 sample, and about 1/3, let's work with decimal places, 1/3 indicated their parents are addicted. But another sample of 500 children, would they give the same answer? Would it result in the same ratio? Or would it be somewhere over here or over here? So when we take multiple samples, that could result in multiple results. So how can I use my own 1 sample to say something about the population, right? I demonstrated the logic behind this, and this is the core logic of inference, sample-to-sample variability, by demonstrating the workings of sampling variability using a software, Fustat, developed by Piet Blokkant, among others. Marianne, you used that as well, right? Yeah. To show that when your sample is randomly drawn, and it's substantially large, the results of all those samples converge, right? Most of the results, when the population is known, will be somewhere around the population parameter when drawing very many samples. And of course, this is something my pre-service teachers had to understand. Thirdly, I was a teacher, educator, and a researcher. I modeled a lesson, and that was called the most frequently used words. What did it entail? The following. In front of my class of pre-service teachers, I had a huge pile of children's novels, many more than this small pile. A huge pile of children's novels, and the question is, what is the most frequently used word in this pile of books? Do you have any idea what would be the most frequently used word in a pile of children's novels? You can say it in English. The AI, yeah? Well, that are likely candidates, right? Well, that's what I wanted to elicit from primary school students, but also from teacher college students. And everywhere I do this activity, they come up with logical candidates. But these are, of course, only hypotheses. And the question is, how can we find out what actually is the most frequently used word? We take a sample, yeah. For you, that's very easy. And actually, for students and even kids, it's not that difficult as well, right? So I listed the need to draw a sample. We can't investigate all words in all these books. There are millions of words. We discuss in what way we draw a sample. For example, each student's one book, one page. We make a top 5 of likely candidates, I and the and a and he and she, something like that. And we count the frequency, how often these 5 words occur in your sample. And we combine the small samples in one sample, large sample, and we use that large sample to draw an inference about the whole pile of books. Yeah, that's the idea of that lesson. So I modeled that lesson because one of the assignments was for the pre-service teachers to use this activity also in primary school in their internships classes and teach this lesson to their kids in primary school. And that's actually what we also did in our intervention. And that's the second part of the intervention, is to prepare and evaluate the ISI lesson in their internship class. Because the 4th study, all those participating students, there were 21, gave that lesson, and in our 4th study, I report of the observation of 3 of them, what ISI knowledge they displayed during teaching. Because in the 3rd study, I showed their ISI knowledge in teacher college setting, but of course that's not what I learn statistics for. Teachers need their knowledge to use it in their classroom, so therefore I went to the classroom, observed the 3 of them, and did a qualitative study. So that's the setup. And let me now turn to the results after I've drank something. Any questions so far? All right, I want to highlight 6 points from the results. I take it all together, all 4 studies. Firstly, the results indicate, in particular the first 2 studies I used for this, that the majority of students tend to use the data as evidence. So that's a good thing, rather than basing their opinion or their conclusions on their own opinions or own opinions. Although a substantial minority did also or only use other sources as evidence. Secondly, what I found out is that the majority of pre-service teachers also is quite well able to describe sample data just for use adequate descriptive statistics which they wanted to use in their inferential statements. For example, calculating or estimating a mean, taking into account or noticing the spread, things like that. Thirdly, when I asked them to design a sampling method, how would you draw a sample from a population, a very large majority showed a preference for non-random sampling methods. Let's see what's over there. Yeah, non-random sampling methods, which have the disadvantage that they could be biased. And I did some follow-up research on this topic with secondary education and university students, and I came up with the hypothesis that it could be due that they feel more control when they do non-random sampling. They have more control on the characteristics of the resulting sample, and then I think it's more likely to be representative. So we shouldn't go over sampling methods too quick when we talk about sampling methods in higher education or secondary education. That's my hypothesis. Yeah, Sietske?
Could you give an example of non-random sampling methods that students prefer?
An example would be I would take as many men as women, as many from North Holland as from Drenthe, which is problematic because there live more people in North Holland than in Drenthe, but that's something they forget, for example. Yeah, they take equal proportions from each category. Yeah, and that's already something that tends to go wrong. And for example, in the pile of books, they were on 3 levels of books. We have A, B, and C level in the Netherlands. And there could be more C books in this pile. We can't see that, right, from over there. But they select 10 from A, 10 from B, 10 from C, for example, right? Okay. During the first 2 studies, so that's the survey study and the exploratory intervention, pre-service teachers showed a preference, they showed an inclination to only describe the sample data. So we asked them to make an inference, first analyze the sample data and then make an inference, but they stopped after having described the data. So we felt the need to, in some way or another, elicit the need to make a generalization. So in the third study, in intervention, what we did was the search for an example in the media. That seemed really to help, to create awareness. Okay, we're talking about inference. And also the model lesson, where there's a huge pile of books which is in view, that helps. Okay, I have my sample, it's only 1 book, but there's the whole pile. So as a teacher, I can refer to the population. Okay, that's your result, but we want an answer for the population. That also helps, stimulates them to make an inference, right? So, yeah, Frans?
But I think also, if you just describe your sample, you say 1/3 of 500 kids said and so on,
Mm-hmm.
then the inference is more implied, and so it's,
Yeah.
You don't feel the need to say, okay, that means that 1/3 of...
You think you're done, maybe, or you maybe mentally you have made an inference, or yeah. But from the first 2 studies, it's either implicit, so unknown. For example, in the survey study, we didn't know whether they only described it, or also meant to make an inference, or we really had to. In the second study, we had to draw it out from them. Yeah. So there's the teacher needed to draw it out. Yeah. But still, it was quite remarkable that they tend to describe it. What was successful as well during the intervention was that the majority of the pre-survey teachers seemed to understand the core logic of inference. So I explained it with a software simulation using Fustat. I explained that the results convert when the sample is getting larger. And what I actually did for primary education, for the teacher education, I took a really large sample, about 1,000, so the results really convert to very small interval, right? It makes it easier. You don't have to make an interval estimation. So the majority understood that. However, when they had to teach in primary school, they found it really difficult to explain how inference is possible and how we can quantify your uncertainty. So primary school students felt there is some uncertainty, but how can you quantify it? And that might be partly due because of the setup of the model lesson, because we have multiple small samples. For example, we have 8 groups of students. I simplify things a bit just for the presentation, right? We have 8 groups of students, and the first groups find as the most frequently used word in their sample the, second he, the, etc., etc. And then we combine them in one large sample. And that's the bar graph over here. In particular, when the word that is most frequently found is close to the number 2, we are really uncertain, right? Okay, it's this in this sample, it's the. In another sample, it could be he, the most frequently used word. So I had a problem explaining that, and kids raised that question. Another sample, it could be he as the most frequently used word. So one solution would be, rather than combining the individual samples of each group, of each student, in one large sample, is by combining the small sample in multiple larger samples, for example, 2 books or 4 books. Again, I'm simplifying things. And then we can show, in some circumstances, when the sample is large enough, that for the largest samples, we find more often the same frequently used words than in the smaller samples. And that's the idea of an inference. The larger the sample, the closer your sample to sample results are. So you have more certainty. So this could help to, if we incorporate this idea of growing samples repeatedly, that could help pre-service teachers or teachers to explain the logic of inference to the students in primary school. To round off my PhD research presentation, the following, we came up with a list of design principles for how to teach informal statistical inference in primary education and the teacher college. But we think these are relevant for secondary education, partly relevant for secondary education and higher education as well. Firstly, I think it's important to first create awareness of inference, as we did in our intervention. Secondly, a general recommendation for statistics education is have students conduct statistical investigations themselves. Let them go through the empirical cycle. When you want to make them inferences as well, then the following design principles become relevant. I think it helps when you use a tangible population and sample, which is really visible, concrete. So the population is a view. It's not all parents, for example, you can't see them. Secondly, use a very large population, an enormous one, so it necessitates drawing a sample. You can't investigate them all. Allow for quick data collection and analysis, because otherwise they spend maybe too much time and energy on their data collection and analysis. For example, in the PowerWorth book, it's very easy to draw a sample, just counting words, and the data analysis is just determining the frequencies of the words. And this holds in particular when you have limited time in your curriculum for statistics or for inferential statistics. If you have more time, of course, you can first do your data analysis, and the next lesson go on for inference. And finally, use repeated sampling, so we can create sample-to-sample variability. Oh, there's a problem. This is my result, but other samples have different results. How can we make an inference about the population? But also use growing samples, small and large samples, so we can see that the sample results converge when the sample is growing, is getting larger. And I think this also marks a bit of the end of the informal part, although it's a bit gray area. What I will do now is move on to the learning path, and what I will distribute 2 handouts. The learning path consists of 4 building blocks. They are in more detail over here. And the learning path runs from primary education to higher education and also vocational education. And the learning path consists of these building blocks. So I suggest take a copy of one for each and have a small reading break of 1 or 2 minutes, right? And then I will present it. All right. In designing this learning path, I used my own PhD research, as you will notice, but also I've done some research on statistics education for the university, and also, of course, use the research on this topic. It's just a proposal, so we can discuss it afterwards. Some notes. These are the 4 building blocks. We'll discuss them in a minute. I've just, because it's an overview, I'll leave out some nuances. For example, I think there should be repetition at each level, educational level. That's not, of course, not in the overview. There are differences between educational levels. Within upper secondary education, we have HAVO and VWO. I ignore them for the moment, of course. Within higher education and vocational education, some studies there is inferential statistics, some there is limited, some there is more. Yeah. I've made a division between humanities, social sciences, and natural sciences. It's just an idea, right? It's just an overview. Okay, so it's built up of 4 building blocks, and as you will see, they reoccur. Many reoccur, and that's because I think it's helpful to, at each level, to have a concrete experience and to work from concrete examples to relate what you're doing statistically with the real life. Moreover, although they reoccur, they are dealt with at a deeper level, so there's the idea of a spiral curriculum of Bruner. For example, in primary education, my learning goal would be that students learn only to make a point estimate. So for a large sample, they're all very close together. Right? So there's some uncertainty, but we're not going to discuss in primary education interval estimation. But that's a topic that will be introduced somewhere in secondary education for most students. That's an example of where we simplify things in primary education by using very large sample. We're not going to discuss small samples and the effect on margin of error and things like that. All right, so we start with analyzing examples of inferences, as I did at the start of my presentation. For example, in the media, that's something useful at each and every educational level. But the farther you get examples of inference in the media, or at work, are becoming relevant. When you're in your internship, listen to your colleagues. What kind of statements do they make? Are there any examples of inference reasoning? How sound is that reasoning? Write a critical report on that. And for higher education, university, maybe also for the VWO, preparatory university education, look at the inferential statistics used in an academic paper and evaluate that, the inferential statistic in the paper. And this example, this building block, it reoccurs and could also help as a tool for formative assessments. Those critical evaluation, when you do it at the beginning, reveals what they know about inferential statistics, what they write down in their reports to what aspects of inferential statistics do they attend. The second building block is explore sampling distributions. That's what I did with the model lesson, with what is the most frequently used word. And the goal would be, and there are 2 steps, A and B. First, manual repeated sampling. That's what I do in primary education. And the goal would be to understand the core logic of inference. For example, with the pile of books. Another example used by Mariana in her research. There are 1,000 balls in this black box. The question is, how many yellow balls are in the black box? Well, there's only a viewing mirror, so we can take a sample of that and we can do a repeated sampling. We get a different number of yellow balls, etc., etc., and we can make a graph like this, right? Also, or a similar graph. And in this way, we can your students are introduced to the notion of sample-to-sample variability, right? And understand when your sample is getting larger, this can be opened. For once, we have a larger viewing window. your sample is getting larger. And what do we see when we do repeated sampling? The results converge. They should converge, they do of course converge. Right? So this is another example of manual repeated sampling and explore sampling variability and also the core logic of inference. And for primary education, I think this is the last attainable part. But of course, this is a bit cumbersome, right? We are limited to the number, to the sample sizes. I think it's 20 and 40 in this example. It takes a lot of time. We want to take more repeated sampling, larger sample sizes. So why not simulate it? And there are many tools available, for example, Fustat, that helps us with that. And I've opened another tool, StatKey. I will come back to StatKey in a minute when I come back to the third building block. You may have all have seen an example like this. We have data, it's from 2014, the Olympic marathon, and 85 athletes completed the marathon between somewhere 130 and 160, 170 minutes. So this is my population. So the population distribution is known, and we can draw samples of size 10, that's over here. Let's draw 10 samples of 10. We see in the large graph the results, another 10, another 10, another 10, around 100. For example, how many do we have by now? Almost 1,000 samples, more than 1,000 samples. So it would take hours to do this with something like this. We can't increase sample size. We can also explore the range. So there's, for example, a two-tail. So 95% of the athletes fall between 136 minutes and 145 minutes. And of course, we're interested in a larger sample size. For example, 50 rather than 10. Draw again 1,000 samples, and then we see that the margin of error is much smaller, between 139 and 141. So the simulations help to explore sampling variability, but it also introduces already some interval estimation, the margin of error. You can quantify your uncertainty a bit, etc., etc. And Marianne shows in her paper, Mathematical Thinking and Learning, how you can proceed from step A to step B, I think, right? Yeah. For example, with the black box activity. And in my learning path, I think that most educational streams, it's relevant to have students explore sampling distributions, right? Because there are many examples of inference or reasoning and inferences in the media and in work life, they should have some understanding of how it works. So they should have a notion of sample-to-sample variability and what is the core logic of inference. And therefore, I've included step of building block 2 in each educational level, also for educational for vocational education. And also for lower secondary education, for example, VMBO, so preparatory vocational education. This building block, this step, ends a bit unnaturally because it ends with, it assumes that the population distribution is known. We now have the data of all 85 athletes. Why would we take a sample then? There's no need for inferential statistics when the population data is known. So, therefore, more realistic is when the population distribution is not known. How do we solve this situation? Because without a known population distribution, we can't create a sampling distribution. We need a lot of samples for that. But we know, traditionally, we solved it in the following way. We know that this sampling distribution follows, when the sample is large enough, a particular distribution. For example, the normal distribution. So when we know that when we know theoretically this is a normal distribution, so we can come up with all those kind of proportions, the p-value. We can create margin of errors, and we need a z-table. However, I don't know how recent your knowledge of inferential statistics is. When we have, oh, that's a pity. I'm sorry about that. Almost there. We now have had inferential statistics. You know of a lot of situations. We not only have one mean, we have two means, we have different assumptions for each, and then we have a small sample, something like the t-distribution is introduced. So we don't not only have the z-distribution, but also a t-distribution, and with the degrees of freedom is introduced, but the degrees of freedom differ from situation to situation. We're not only interested in continuous data, but also in categorical data, so we need chi-square distribution. And this is what happens to our students. Booms, do they had say. Students have difficulties understanding inferential statistics at university or maybe at University of Applied Sciences, right? So about 10 years ago, an American statistician called George Cobb in 2007 gave a speech and he said, we have computers now. We can do simulations and to solve the problem, we only have one sample, how can we make an inference about a population? Because he also saw that the many problems students have with the traditional method based on probability distributions, like the normal distribution with all those exceptions, etc. And you can use simulation-based inference to create confidence interval and do hypothesis testing. And simulation-based inference is based on resampling. And since 2007, research has been done whether this indeed helps. And the idea is it's more intuitive, it's more easier to understand conceptually. And evidence shows indeed it helps students, preliminary evidence shows it helps students to understand the basics of statistical inference. And resampling, so that means not repeated sampling, because you only have one sample. Resampling means resample from your one sample. So that's bootstrapping, for example, and permutation tests. Familiar? I'm not going to discuss it in detail. I can do it later on if you would like to. But there are a number of advantages. Let's see. Yeah. There are a number of advantages. You don't need so many formulas and procedures. Resampling means, so it's drawing a sample from your sample with replacement, and it's similar to repeated sampling, what we do over here. So it's very similar, it's very visual. You also use, for example, StatKey or FuStats. You can do bootstrapping. So the process is similar. So you keep your eyes on the data, you keep your eyes on the sampling process, rather than being focusing on the formulas and focusing on the tables with all the exceptions and on the calculations. It applies the same logic applies in multiple situations, so you don't need all those formulas and all these tables. Other advantages, let's see. It requires fewer steps. And so that were all the conceptual reasons to think it might be beneficial. And indeed, the evidence shows it seems to help students to understand statistical inference. In particular for weaker students, but also I think it's good for stronger students, because when students go on in statistics and go to advanced statistics nowadays is often based on simulations rather than on parametric approaches with probability distributions. And I think it's a nice bridge between the traditional approach with the probability distributions and the really informal approach with the hands-on manual repeated sampling. And there are textbooks available nowadays based on simulation-based inference. For example, let's see, Statistics Unlocking the Power of Data. It is written by Lok, and Lok. That's actually a family of 5, a husband and his wife, and 3 of his children have written this book, and it's a really great book. It's a digital book, and I worked with this book with students in my research project, exploratory research project, and I love this book. They have a lot of digital tools. It's very easy to use, and well, my students really were enthusiastic about it because it helped them to understand the statistical inference. And I think for secondary education, this could be a very good approach. So for upper secondary education, rather than using probability distributions, the normal distribution, T distributions, I think this would be a very great approach. Also for universities of applied sciences, who get some inferential statistics, could be beneficial. For humanities, those humanity studies that require some inferential statistics could be good approach as well. Finally, the traditional approach based on probability distributions, well, that's easier to understand when you first have simulation-based inference. That's the contention in the literature. And still, for some students, it's relevant to learn a traditional approach. For the mathematically strong students to understand the mathematics behind the statistics, but also because it's common practice still in academia to use this approach. So you have to work in that world. So it's good to learn that. And finally, another reason is that it applies in more situations than simulation-based inference. So not for each and every situation, simulation-based inference works. And I think I discussed most of this. All right, I started with the question how to teach inferential statistics. And I came up with a learning path, starting from primary education, very informal, all the way up to vocational and higher education. Well, I'm curious to hear about your thoughts about it, but I hope it helps to to raise statistically literate citizens and to have less anxious students in higher education, less statistics anxious students. So thanks for your attention, and feel free to ask questions. Thank you.